Hello and welcome to today's lesson on current and fields. Our learning objectives are to describe how to show that a current can create a magnetic effect, describe the direction of the magnetic field around a conducting wire, recall how the strength of the field depends on the current and the distance from the conductor, and explain how solenoids can enhance the magnetic effect. We're now going to look at a very important experiment by someone called Hans Christian Ørsted. When magnetism and electricity were first discovered, it was assumed that these were two completely separate phenomena. It was only in 1820 when Hans Christian Ørsted, quite by accident, discovered that when he had an electrical wire with current passing through it near a compass, it would cause the compass to deflect. He discovered the fundamental connection between electric current and magnetism. Ørsted discovered that if you had current flowing towards you, then the magnetic field around the wire would be in an anti-clockwise direction. If the electric current was travelling away from you, then the field lines around the wire would be in the clockwise direction. If you have an electric current passing through a wire, it will generate a magnetic field around it, and you can see where those field lines are by placing plotting compasses around the wire. And in the diagram here you can see how we represent current flowing towards and away from you on the page. If the current's flowing away from you, then we mark it with an X as if it was a dart going away from us and we just saw the fins at the back of the dart. And if the wire is bringing the current towards us, then it has a dot which should be reminiscent of the spiky end of a dart coming towards you. If you need to work out which direction the magnetic field around a wire will work, using your right hand you can place your thumb in the direction of the flow of electricity and then wrap your fingers around the wire, and your fingers will wrap around the wire in the same direction as the magnetic field, as you can see here. What we've seen here is the basic principle behind an electromagnet, but what could we do to make the magnetic field stronger? The strength of the magnetic field is called the magnetic field strength or magnetic flux density, and it depends on two things. The size of the current flowing through the wire and the distance you are away from the wire. Magnetic field strength is measured in Tesla. To give you an idea of the size of a Tesla, 0.01 milliteslas is about the strength of the Earth's magnetic field. The strength of a field about 1 centimetre from a wire carrying a current of 5 amps would be about 0.1 milliteslas. A strong magnet near its pole would be able to generate 1 Tesla. You can make a magnetic field even stronger by looping the wire over again and again and again so their magnetic fields overlap. An electromagnet with multiple loops of wire is called a solenoid, and it produces a much stronger magnetic field than a single wire on its own. The field lines around a solenoid are just like the field lines around a bar magnet. You can make a solenoid even more powerful by putting a magnetic material inside the coil, something such as a soft iron core, which when it's put in the magnetic field of the electromagnet will itself become an induced magnet and therefore make the whole system more powerful. We're now going to look at an experiment that you could do yourself at home, and that is to test the power of an electromagnet when you change one of the variables. So here you can see there is a simple switch, a battery or cell, a nail and some wire wrapped around the nail, making a solenoid or electromagnet. In addition to the apparatus we've already mentioned, you'll also need some paper clips. So to start with, we'd connect the coil of wire to the power supply and then check that it acts like an electromagnet and is able to pick up the paper clips. And then we'd have to investigate whether balancing the paper clips in a single line or counting the total number of paper clips we're able to pick up would give us the most repeatable set of results. Here's an example of the type of results table we could use, with the number of coils of wire on the left hand side and the number of paper clips lifted on the right hand side. We could also investigate changing voltage. We would expect to see that as we add more coils of wire, the power of the electromagnet would increase, and so the number of paper clips picked would be larger. For the next few questions, please pause the video at each question and then write your answer in your book. To start with, state the name of the coil of wire which has many turns and carries a current. Pause the video now. It would be called a solenoid. Please tick it if you've got it right and correct it if you haven't. What could we use other than a compass to show the magnetic field around a wire? We could scatter iron filings over the area around the wire. In the experiment we described using the electromagnet, what was our independent variable? It was the number of turns in the wire. Why is the strength of the magnetic field between a loop of wire stronger than the field due to a single wire? The two fields would add together. What was the dependent variable in the test we described? It was the number of paper clips that the electromagnet lifted. State one controlled variable for this experiment. You could have had the size or the mass of the paper clips, and you could also have had keeping the potential difference the same as well. What would have happened if we increased the potential difference across the electromagnet? The strength of the electromagnet would increase. What would happen if the soft iron core was removed? The strength of the magnetic field would be decreased. Explain why the iron core strengthens the effect of the electromagnet. The iron core becomes an induced magnet. Right, well that brings us to the end of today's lesson. Thank you very much, and I hope you found it useful.